Now, with using the calculator, it's like it's guaranteed that you can get some points. I don't know if you can get the pattern, but guaranteed you can get points. Guaranteed. That's not enough. But not enough. Good start, but not enough. I'm not going to do any graphing for you yet on this. Not yet. Not yet. Now, with your calculators, you ought to be pretty confident of your answers. Wait, Cliff, your graphs are as bad as mine are. Look at that x-axis go down there. That's as bad as mine is, too. Now, what do you think my next question is going to be before I do anything of explanation? What do you think? My next question is going to be to ask you to do what? Inverse. Okay, so here's what I want you to do first. Find the inverse of the log function. So you've got to write that. Now, you already know what the graph looks like, probably. But then I want you to graph that also. Yeah, and some people have already sketched in that y equals x. That's a good idea. Sketch in the y equals x. That's a snap. Now, you know what's going to happen with the inverses around that y equals x. But what I want to see written on your paper is the inverse log function. Actually get that written. Nikki, you got to be a little more careful there, I think. Do you really have a point right here?
Yeah.
You do? So you got to... I don't think so. I think that's what happens. -1. Now, where'd that come from? Well, put 0 in. Is that what you're doing? Putting in 0 and then finding the log of 0?
No.
See, that gives you an error.
Yeah, but if I put 0.1 into x...
Okay. Okay, sure. But 0.1 would be like just over here, just a little ways and then down, right?
Yeah,
right?
Yeah.
I mean, to me, that shows a point on that y-axis. I think, Molly, that's probably correct, yeah. Oh, do you think so? You did? Did you get minus? Okay, what's that say? Go over x for 0.1 and go down. See, yeah. So you've gone over and down. Now, okay, it's you know, what happens? It's going to run right along that y-axis. It can't cross it. That's right. It can't cross it. Now, I'm not sure. I'm not going to say that yet. I'm not going to say that yet. Now, I've been rather precise in my question, though. Graph the log function. Don't forget now, folks, in a little bit here, you've got to convince me that what you're doing is correct. And don't lose sight of what we started with, the log function. log function. Now, you sure you can convince me? Because obviously your graphs look good. I mean, they are inverses of each other. They go around that y equals x line. Nate, there's a little more to both of the graphs, Nate, and you can do that with your calculator, too. Ooh, be careful now, Nate. Now, ask your calculator, Nate. Ask your calculator. I mean, your calculator's going to... Can you convince me? Because, Jill, obviously you're going to say those are inverses of each other on the pictures, on the graphs. Ah, boy, I don't know, Todd. I'm not sure what's this right here. Is that 0 there? Is that? I don't think that's what comes out of your calculator. Yeah. Now, what do you think that means? What's your calculator telling you? It's telling you something there. Now, you're pretty sure those are inverses of each other. Okay, now do you have the inverse equations of each other? I know. Now you got to finish that off for me. I'm not going to let you stop there. was it yesterday or the day before that I talked about what log means without a base? We talked about that, remember? What's it mean? Base 10. Well, that'll help you a little bit. Okay? So it's a base 10 problem because I made a big deal of the log function. So it is a base 10. That ought to help you on that next one right there. You got to go? Okay. Try and walk out without falling over anything, okay? Yeah, that looks good. 10 to the x equals y, and what was the first one? What is that? Yeah, what equation? What equation? That goes log of x. All right. Now, I think as I've seen graphs, they're correct, but I'm not terribly impressed with that because your calculator did a lot of the work for you in the beginning, and then once you had the first graph, we know what happens with inverse graphs. You got an extra twist in there. It's kind of a neat-looking graph. I've got to admit that. There's a nice kind of neat-looking curve in there, but I don't think that's right. As a matter of fact, what's probably going to happen is they're actually going to cross over that line up there, aren't they? I think they get further apart. I'll do them on the calculator in a minute. I don't want to do that yet, though. What was the first equation that I asked you to graph? Someone tell me. What's the first equation that I asked you to graph? Say it again. Y equals log of x. Okay. Everybody agree to that? Now, I'll write this in white chalk. We know that when there's nothing written here, and it's the word log, that it's a 10 that in fact goes there. Is that correct? All right. Someone tell me what was the inverse of this, the equation. The equation. We'll go ahead. Okay. Go ahead. Thank you. Thank you. Well done. Whew. Y equals. You said 10 to the x. Yeah. Yeah. Okay, Cliff. Now let's. Okay, Cliff. You got it. Now, where does it come from? What's the first step in finding the inverse? Switching. Yeah, switching the x and the y. So I'll start right up here with x equals log y. But then what do you have to do next?
Put it in a y equals.
Sure, solve for y. Now, how do you solve that for y, Cliff? What's Joe going to say? Go ahead, Joe.
Definitional logarithm.
Yeah, definitional logarithm. Now, Cliff, really, there's a 10 written right here, isn't there? So how do we rewrite this without the word log in there? We go 10 to the x equals y. Do you see what I'm saying? Okay, is everybody by that now? So you see that these are inverse functions of each other. Now, remember, that's a part of the problem that I asked you to do, was to write those equations. Now, Marcel, I want to start with looking at this equation because I think that's going to be easier for me to explain to you, the little problem that you have right there. Okay. Marcel, we probably got to start with x equals 0. What happens with x equals 0? Ooh. Marcel, you're killing me here. Now, Marcel, look, I'm on the y equals 10 to the x, okay? And I'm going to come down here and do a quick little table. We'll put a 0 right in there. What's 10 to the 0? Ah, big deal. So that thing does go through 1 right there, doesn't it? Now, most of these equations like this with an exponent here as a variable are going to go through 1 because when that is 0, that whole thing is going to equal 1. That's okay to there, right? Now, let's let x get bigger. Let's go like to 1, to 2, to 3, to 4. Now, as x increases, what's going to happen to y? Quite quickly, right? Ooh. Well, let's try 1 right here. What do you get? Yeah, let's try 2. There it goes. Boy, that's a jump. 3. That's a huge, I'm way off any graph I would ever do. And you see what's happening? Isn't that thing just flying up there? So what's the graph going to look like? Yeah, upward curve, but a very quick upward curve. Now, there's no kind of floating around up there. You see what I'm saying? It's not going to start doing anything like that. As this x goes over here bigger and bigger, that y is going to go up very, very quickly. Do you see what I'm saying? Now, you've got that extra little loop in, I think, in both of your curves. That kind of takes that. Now, listen, can x be negative? You sure? How come? Well, that was quite a sentence. That's not bad, incidentally. That's not too bad. Okay, but remember, I'm going to say that I'm doing an exponent equation here. So for a moment, I'm not going to worry about a log equation. Now let's come back to this one here. Now, can x equal negative 1? What do you get when you get x equals negative 1? What's y? Sure, sure. And negative 2? Yeah, now what's happening then right down here as x gets smaller and smaller and smaller? Yes, guys, will it ever equal 0? No. Got a fancy word for that. What's it called? Asymptote, that's right. So Marcel, this graph is going to come down here like this and get closer and closer and closer to that x-axis, but technically speaking, it's never going to hit the x-axis. Does that make sense to you? That graph looks good then, doesn't it? Can you see that your log function, the one that's an inverse, then isn't really quite correct because of what I have up there and what we know we're going to get when we bring that around the y equals x line? Okay, does everybody like that graph there? Let's see if I can do this graphing now. This will be a miracle here. I forgot my glasses. Well, I'm in trouble already here. Let's see. I can at least turn it on. There it is. Y equals. Now, what's the first one I asked you to graph? Was it log of x, right? Okay, now help me read them. Is up on there? Does that say log x? Okay. Watch this thing go now. Now, there's your graph. There's your graph. All right? Now, you know, this thing does not go up very fast. I tend to, when I draw them on the board, I think, make them move a little bit too quickly. Now, I had to set the range on this. Have you tried this yet on the graphing calculator, John and Casey? The problem that I had was getting a range. Now, look what my range is. I only have x going from -3 to 3 and y going from -2 to 2 because, John, what I was getting was such a tiny little bit of a graph when I had the 10 and -10.
Graph log.
It does. It builds a range in for it. Okay, so you get a good look at it then. Yeah. Now, what happens then when you try the y equals 10 to the x on the same one? Will that go okay? Mine doesn't go real good. Now, let me try that next one now. Y equals 10 to the x. So there's a 10, and here's to the x. And we'll try this graph, and you know exactly what's going to happen. There's the first one. Now, here's the exponent one shooting right up there. And that one, in Marcel, you can see that one going up very, very quickly. You know, if I back out to take a bigger picture of this thing, this is going to be going up almost straight in a heck of a hurry. And then we ought to do the y equals x on here to see what that's going to look like. 1, 2, 3, and here's y equals x. And now we'll graph all of them. And look at that. There's the first one. There's the second one. And there equals y equals x, and they certainly are inverses of each other. There's a real good picture. Ooh, isn't that neat? Yep. Questions? Now, Marcel, is this thing ever going to take a dip up here? Marcel, is this thing ever going to take a dip out here? Marcel, will it ever cross that axis? Say it again. Nope. Marcel, will it ever cross that axis? Nope. Marcel, will this thing ever dip down again? How do you know? I mean, your answers were exactly correct. How do you know? Any idea? Marcel, why don't we try looking over in here? Now, as x gets bigger, okay, on this graph, what's going to happen to y? That's right. That's right. Now, that's what guarantees you that there's no sudden dip on there. There's no way the thing can start coming back down again. Right here, as x gets smaller, now when I'm saying smaller, away from 0 to the left, okay, more negative, what will happen to y? It's going to get smaller and smaller, but it'll never get to 0, will it? Now, what happens when we draw it? Well, we're going to touch that axis. I mean, it's hard to stay away from it. But technically speaking, it never touched that axis. Casey and John, what do we call this stuff when we're doing in the calculus here? What's the word that we use as we talk about that getting closer and closer to? We had a fancy term for it. Limit. Yeah, we're talking about limits. So when you guys get into the calculus, we'll go away from an asymptote and we'll start thinking about limits and what a limit is. And this is a nice picture of a limit. So what I would say, the limit here is 0. Does it ever get there? No. Does it get closer and closer to it? Yes. Go ahead.
I don't know if it's just because they're I don't know if you start doing really big numbers and then do the log, it keeps giving you 10 for the log.
Yeah, I think what happens is that you probably get past the capability of your calculator in a hurry. In a hurry. I mean, these numbers they're going to really take off. So my sense is that you're going to get past the capability of the little calculator they have. And this will happen on the graph somewhere along the line too. I don't know quite where, but it'll happen. Okay? Others. Well, I think you have on your calculator this key called LN. Am I correct? Not LOG, but LN. That's the next thing I'd like to do with this morning's lesson, if I can, and talk about this thing called LN. Now, what we have seen is that there are some logarithms that have a base 10. Why do you suppose they had logarithms with a base 10? That's right. Base 10 number system, we had 10 fingers, okay? And we're pretty used to working with 10s and multiplying with 10. So that's probably the reason that they had these things called common logarithms, base 10. Sometimes you work with logarithms to the base 2. To the base 2. Any idea why the base 2? It has to do with computers, it has to do with calculators, it has to do with binary, yeah. Why is the binary system used an awful lot, though? Yeah, that's maybe a reason. Yeah, it is simple, and it is just zeros and ones. Go ahead. There you go. Switches. Switches are on or off. Yep. So it comes out of the electricity and the fact that switches are basically on or off. And that's a reason for using the log 2. Now, we also have this other thing that we run into in calculus. And we're going to do that just a little bit, Casey and John. As we run into calculus, we run into this thing called a natural logarithm. And a natural logarithm is the letter E. Now, it's a little bit like this pi number. Pi is kind of a neat number. It's a constant, isn't it? Now, does pi have an exact value? No? I thought it was 3 1/7. I thought it was 22 over 7. Yeah, that'd be exact, wouldn't it?
It's an irrational number.
Well, what about this 22 over 7 stuff then, Chris? Is it approximate? But Katie, 3 1/7 isn't approximate. That's right. That's right there, Nick. You got it. Yeah. Yeah. Tell me, guys. Come on, pi. I didn't think we were going to be talking about this for so long. Say it. Yeah, it is. 3 1/7 is pi.
No, because if you do it on your calculator and then you press the pi key, they're different.
Let's try it. Thank you very much, Evan. Good thought. Good thought. You guys got a pi key in your calculator. Get it up there, pi. Now compare that with 3 1/7. I don't know how you're going to compare it. I know how I would, but. Okay, and then compare the two. Now they are a little different, aren't they? Yeah, yeah. Say it again?
Round off.
Round off error. That's neat. Round off from where?
Either one.
From either one.
From the entire fraction, because the decimal can't be exactly the fraction.
Say that again?
A fraction got to be, it's exact, it's all right there. It's just like, even though you can't write it as a decimal, it's still exact.
Yeah, man.
I'm not sure what that says. Not sure what you're saying. You may be right. I don't know what you're saying.
No, if the number doesn't.
He's saying that whenever you ask for exact values, you always do a fraction.
Well, first, I guess the first thing you're seeing is that on your calculator, you're not getting quite the same thing. I mean, that's first is clear, all right? So I guess my question that I'm asking you, Nate, is this correct right here? Now, Chris called this number a...
Irrational.
And Chris would call this number?
Irrational.
Say it again?
Irrational. No, rational.
Is this rational?
No.
Let's start there. Yeah, yeah, it is? If it's a fraction, sure, thank you. And that's 22 over 7. What's a rational number? Quotient of two integers, right? So is that rational? Yes, got to be. Now, Chris, you still want to call this one irrational, don't you? Now, Chris, can an irrational equal a rational?
No, they're not equal.
No way, they're not equal. Okay, that's what you're telling me right now, that they, in fact, are not equal. Now, Nate, I believe that as you've studied pi, that you've used that number, you've used 22 over 7, you've used 3.14, and maybe you have some more numbers, remember, and I guess your calculator probably goes out to 7 or 8 places. Now, Nate, is there an equality between these two things? No. That one is irrational. Chris is exactly correct. What is this, then?
This has to be rational.
Say it again?
It has to be rational.
Yeah, but is it pi?
It's an approximation.
There you go. That's the exact word I want to say. It's an approximation of pi. Do we have some approximations of pi? Yes. Do we have an exact value of pi? No. Todd, where's pi come from? Uh-oh. Mike, where's Todd? Where's Todd come from? Mike, where's pi come from? Let me ask you a different question then. Do we use pi very much? When? Circles, there you go. When dealing with circles. Finding what of a circle? Circumference and?
Area.
Area, yeah. Now, we've used pi in trigonometry, haven't we? When? we've had ratings, we've talked about pi over 2, pi over 3, 5 pi over 6, and so on and so forth. So pi is something that gets used quite a bit in the study of mathematics. Todd, where's pi come from? Yeah, where's it come from? From the circumference of the circle.
Circumference equals 2 pi.
Say again, please.
Circumference equals 2 pi.
Circumference equals 2 pi. That'd be fascinating, because that means every